Talk a little bit about what I believe you should have taken away from what you just saw and what I gave you as a definition. A projectile is an object that moves in two dimensions but experiences an acceleration in only one. So if you consider the launch we just did where we tipped the projectile upwards and gave it a launch velocity at an angle relative to the horizontal. We saw the projectile travel with a path that looks like this. Good so far? At the moment of launch, the object had a single launch velocity and angle. I'm going to write the word launch here because I used to write just V with a V naught there, but students got confused about that. This is the launch velocity. But the truth is, because we are learned people, the object had two components to its velocity at launch. There's the horizontal component of the velocity at launch, and there was the vertical component of the ball's velocity at launch. So our single launch velocity and angle can be broken up into part of the velocity's motion that's horizontal and the part of the object's motion that's vertical. Now, if you go back to what I just said, a projectile is an object that's moving in two dimensions but is experiencing an acceleration in only one dimension. So one of these is being acted on by gravity and one of them is not. Is it pretty obvious to you which one is which? So let's see if this one was, say, 2 meters per second and this one was 1.5 meters per second, and we trace the object's path until we reach here. Can we agree that there's going to be a velocity this way and a velocity this way when it reaches the ground? Does that make reasonable sense? How fast is this one? It has to be 2 meters per second. That's right. In fact, I intentionally didn't draw the arrows the same size so I wouldn't lead you, but yeah, that arrow should stay the same size because the object's horizontal velocity will never change through the course of its motion because there's no acceleration in the horizontal direction. Now, if there was an acceleration in the horizontal direction, you could still work the problem. Like say the wind is blowing in the horizontal direction, you have a wind this way. You just have two different accelerations, one affecting the vertical, that's gravity, and one affecting the horizontal, that's the wind. But we're not going to do problems like that. Our problems are going to be very straightforward, that there's no horizontal acceleration and only a vertical acceleration. Is the ball's velocity ever zero? I'm seeing you have more mixed emotion there, but the answer is no. At the very top, it still has a horizontal velocity of 2 meters per second. As we said, the horizontal velocity is unaffected as it moves. So its velocity there isn't zero. It's one of its components of velocity is zero. But the other component is never zero because it was launched with a horizontal velocity. So the thing to think about here is the object has two parts to its motion. It has one trajectory. This red line is what we would call the trajectory. It is the path that the projectile takes. That is the trajectory. So as a vocabulary word goes, if you didn't know that, the path of a projectile is called the trajectory. And we will prove later this unit that the trajectory is a parabolic path. That's not an arbitrary path, that this path is a parabola. But we can break the object into two kinds of motion. Consider if I stand directly behind this and get myself eye level with the motion, and I close one eye, and I look at the ball's motion, and it's amazing to know if you just closed one eye. Thank you for that, appreciate it. Use the power of suggestion, pretty powerful. I wouldn't necessarily know that the ball's going that direction, because I lose my depth perception when I close one eye, but I could just see the ball go up and back down. The y velocity and the y motion of the ball is just going to be up and down. While if I could get up onto the ceiling and look down on it, same kind of idea. I would just see the ball traveling at a constant speed along the crossroom, right? As it just goes that way. Probably stayed at that speed once it hit the ground. Because even though it hit the ground and stopped going downwards, its horizontal velocity was probably unaffected until it hit the back of the classroom. So when we talk about a projectile, the horizontal components aren't changed, the horizontal velocity is not changing, but the vertical one is. That suggests I should put a little 0 here to indicate that the y velocity will have an initial value that's not going to stay the same. In fact, let's consider things we do know about this problem, like the idea that it started here at this location and ended down here, right? In the vertical direction, it started at the top of the table and ended at the floor. I know that the actual landing was over here, but if I'm just thinking about the vertical portion of the motion, this is the vertical displacement of the projectile, which I will label delta y, vertical displacement. And at the same time, it had a horizontal displacement. I'll label that delta x. Now, when I consider, again, just bringing together the stuff I suspect you already know, in the vertical direction, there's going to be the change in height of the object. There's going to be the initial velocity of the object, but just in the y direction. There's going to be some final velocity of the object, because we know it changes because the object is experiencing an acceleration. Right? An acceleration in only one dimension. In fact, this is probably going to be g, acceleration due to gravity. At the same time, there's going to be a horizontal direction. And it's going to have its own components, its own information. Like there's going to be the horizontal displacement, delta x. There's going to be a horizontal velocity, but that stays constant. So I don't have to put initial and final. It's going to be the same value at start as it is at the end. Now, the thing that you have to understand about a projectile is that it still only has, at any one time, one velocity. Right? And that red path is the path that it's taking. So it's traveling horizontally while it's traveling vertically. And although we can break up that study into two distinct sets of components, it's still only traveling along one path. And what I mean by that is it goes up and down in the same amount of time it takes to go left to right. So the thing that links the problem together is that the time it takes to do this has to be the same. And what I've drawn for you, I think, is a chart that you should make every time you're faced with a projectile problem. Because a projectile problem is going to present you with a certain amount of information. And it's almost twice as much information as a regular one-dimensional motion problem. Why? Because you've got 2 dimensions. So, 2 sets of information. But what ties the problem together is time. The time it takes to go up and down is the same as the time it takes to go side to side. That's what links the 2 parts of the problem together. How about we try one of these out? Is that okay with you guys? Before I do so, I need to show you one more little thing. I think it's tiny, but if I don't show you, I think I'll have trouble with some of you, okay? Let's talk about this for a minute. I'm going to clean this up so it's got fewer distractions. Get rid of this little red line here. There we go. And even, let's get rid of that and that. There. No distractions. Now, the ball is going to be launched at some angle. To me, it makes sense to consider that we need to provide reference so that we can have an agreed upon origin and way of doing measurements. And I think it makes perfect sense to establish this as the x direction and this as the y direction. That makes sense? If I do so, and I provide you with the launch velocity and the launch angle, you could wrap a triangle around that angle, and that triangle would be the horizontal launch velocity and the vertical launch velocity. Correct? Those are the components of the object's velocity. And if I look closely at this, based on the angle I was given, and which one of these sides is the opposite and which one is the adjacent, this has to be VL sine theta, and this has to be VL cosine theta. Right, that would have to be true, assuming we make the horizontal direction the x direction, which I think makes reasonable sense. So when I consider our little chart here, I think one thing we could put into this chart is that this is always going to be VL sine theta. This is always going to be VL cosine theta for as long as the horizontal is how we measure our launch angle. And I think it's probably reasonable that we will. Be aware, launch angles can be positive or negative. You can have a declination or a launch angle that's negative. So be mindful of that when it comes to sine, because sine is positive in the first quadrant and negative in the fourth quadrant. That would be a negative launch angle. All right, ready to do an example? Yeah.
What does the L stand for?
Launch. Is that okay?
Yeah.
So we're going to do a simple example with the time that we have left, and I believe we will have enough time to complete this one example. I'm going to give you a kind of a slow ball for this one. It's not particularly hard. Let's assume we go back to the first example I did where I just launched the ball horizontally. That's a launch angle of 0 degrees. I don't know if you noticed, but the ball landed over there where between the legs of the second table. So when I measured that during first period, that was about 3.5 meters away from my table. So the ball had a trajectory like that. We measured my table with the meter stick, and the launcher plus the table is about 1.2 meters from the floor. I'd like to know what the launch velocity was of the launcher. Everybody understand the parameters of my problem? Step 1, I think you should make a chart that contains the information you're going to use for this problem. I think you should have a vertical side and a horizontal side. And in that chart, you should populate it with the information you're going to use to solve the problem. Sometimes delta x is called the range too, so I want to make sure I've said that. In the example that we're talking about right now, we are given the range where it landed, 3.5 meters away from the front of the table. We know delta y. The ball landed 1.2 meters below where it started. So my delta y is 1.2 meters. Yeah, go ahead.
Would it not be negative 1.2 meters?
Well, I haven't gone to that point where I signed direction yet, but that is one of my steps. So my step 1 is to draw the chart and populate it. But you raise a good point, because although the acceleration is 10 meters per second squared, step 2 should require you to decide what direction you're going to make positive and what direction you're going to make negative. So do we want upwards to be positive or negative? Okay. And do we want to the right to be positive or negative? if we make those two choices, then yeah, the 1.2 has to be made negative and the 10 has to be made negative. But the 3.5 can stay positive. Now, Vy naught is VL sine theta, and Vx is VL cosine theta. When I put 0 in, cosine becomes 1 and sine becomes 0. Correct? The sine of 0 is 0 and the cosine of 0 is 1. We're all good there? That means my initial launch velocity must be 0 in the y direction. And VL is equal to Vx in the horizontal direction. All good? Go ahead. The sine of 0 is 0. That makes the initial y velocity 0. But the cosine of 0 is 1. That means that the horizontal velocity is just going to be whatever the launcher launched it at. That good? All right. So now, if you'll look, do you see that you have a pathway to figure out the time? We need at least 3 pieces of information here to use one of the motion equations. And since there's no acceleration, we need at least 2 pieces of information here. In this problem, you're always looking to see if you have 3 pieces of vertical information or 2 pieces of horizontal information. But there should be a pathway to figure out the time on one side and use it on the other. I think there is one here.